All right, everybody, welcome to this week's GOCC. I think there'll be a couple people still jumping in. Welcome. Before we get started with the talk, I'd like to remind everybody of our community statement and our kind of guidelines. The first one is we are all learning, and so no question is too basic, too standard, so please feel free to use the chat, and Alex will be monitoring that today and asking it during the out loud for you all. And then afterwards, you all can unmute yourselves and ask for the sake of the recording. The second one is everyone has something to contribute. And so share your little bits of knowledge if it seems appropriate. And then the last one is no one has all the answers, not even the speaker. And so we can make an effort to answer the questions, using the chat and combining our brain power, or we ask experts afterwards. But I'm sure that this will be a great talk. So let's get started. Today we have Matias von Bell from the University of Kentucky, and he will be talking to us about Schroder, Combinatorics, and the nu-associahedron. So let's welcome Matias.
Thank you, Andres. Thanks for that. It's my pleasure to be talking with you today about Schroder combinatorics and the nu-associahedron. And yeah, as Andres said, if there are questions, Alex can interrupt me at any point. So please do that. Yeah, so Schroder combinatorics and the nu-associahedron. This is based on an archive preprint currently on the archive that's also with the same name, and this is joint work with Martha Yip. And we'll begin by talking about some background and motivation, then generalize some Schroder paths and some classical results into this new Schroder setting that I will describe soon. And then we're going to describe the connection between nu-associahedron and new Schroder paths. And then finally, we're going to use this new Schroder description to prove something about the nu-associahedron, namely that it's contractible. And so it'll be kind of an interplay between some geometry and enumerative stuff today. And yeah, so let's begin with some classical background stuff. So small Schroder numbers, also known as Schroder-Hipparchus numbers, are 1, 3, 11, 45, etc. And they count many well-known objects, including dissections of an n+2 gon, faces of the associahedron, and also lattice paths with northeast and diagonal steps, where they stay above the line y equals x with no d steps on the line y equals x. So down here below, we have a two-dimensional associahedron, which is of course a pentagon, and its faces there are indexed by the small Schroder paths there. And so the condition that no d steps are on the line y equals x, that can be seen as no d steps occur in those dark gray boxes. So that's a very classical case. And the generalization that we're going to be looking at today is the following. So we start with a lattice path from 0, 0 to BA, and a new Schroder path is going to be a path with steps northeast and diagonal steps from 0, 0 to BA that stay weakly above this lattice path nu. So this lattice path nu here doesn't contain any diagonal steps. It's going to be just north and east steps. But then a new Schroder path is going to be a path that stays above that path nu, where we allow these northeast and also diagonal steps. And then in the case that there are no diagonal steps in this new Schroder path, then that's a new Dick path. And so for any arbitrary lattice path, we can then define these new Schroder paths. And if you know, if you've looked at anything related to Schroder paths in the past, And as hinted by the fact that I just talked about small Schroder paths, there are also large Schroder paths. And these are ones where we drop the restriction that they can't have any d steps on the diagonal line y equals x. So in this case, we are allowed to have these diagonal steps occur in these gray boxes, which corresponds to being on the line y equals x. A cool theorem that is known about these large Schroder paths in the classical case is that the set of large Schroder paths can be partitioned into two halves, where one half is a set of small Schroder paths and the other one is the paths that contain at least one d step on the diagonal line y equals x. And so this was also generalized a bit further by Gessel, who extended it to Schroder paths that stay above a line from 0, 0 to mn, comma n. And so for the case here where n is 3 and m is 2, we can see in this case that this would be a large Schroder path, because it still makes sense to talk about what it means to be on the diagonal here, for a diagonal step to be on this diagonal line, because it would just have to touch it there at any of these 3 points that I just marked. But then if we go to new generality, it's not as obvious anymore what the diagonals would be. So we ask, can we extend this to new generality, this sort of relationship? And the answer is yes, but we have to generalize this notion of what it means to be on a diagonal line first.
I have a question about this theorem. So as written, so it seems like this is just an automatic truth. Is the idea that there's like a nice way to partition them that you haven't described, or am I missing something? Because it seems like this is just like a tautology, but I assume that there's something hiding behind it that you're not explaining.
You'll see the proof in just a second, which generalizes that, and I think then it will become clear why.
I think the reason it's not a tautology is because it's half meaning like actually half of them.
Oh, like actually half.
Yes.
Okay.
Partitions
Okay.
it into.
I read that as like a vague sense of like parts. Okay, that makes total sense then. Thanks.
Right. So the set of small Schroder paths is half of the size of that is half of the cardinality of.
Okay. Yes, that is an interesting result. Then I understand.
Okay. Yeah. All right. So yeah, good question. So the diagonal then is the boxes under the. We're going to define the diagonal to be the boxes under the peaks of nu. So a peak is a northeast consecutive pair. So they are actually what we've been shading in the dark gray here. They are the boxes under these peaks of the new diagonal, or sorry, the new path. And so those are the ones that you're allowed to cut through in a large new Schroder path. And it matches up exactly with the classical case and the diagonal case if we define it this way. And this, I guess, rectangular case in the middle. So a large new Schroder path then is allowed to have d steps on the new diagonal. And so then the way we generalize that, or with this generalization, the following is true. So this is stated exactly, excuse me. This is stated a little bit more clearly than the previous one that I had put up there, is that the cardinality of the large new Schroder paths is twice the cardinality of the small new Schroder paths. With this extra condition that this is true if and only if nu begins with a north step and ends with an east step. So here's the proof for that. And this is essentially just a generalization of what Gessel had already done in the rectangular case that we just saw. Here, if we define a map from the set of small Schroder numbers, or small Schroder paths, to the large ones without the small ones. So what that ends up being is one's paths with exactly one step, or at least one step on the diagonal. And we define this map as follows. So we take a path, it begins with a north step, that's one of the assumptions, and then it has a east step, a first east step that's on the new diagonal. And those two are the steps that we're going to delete and replace one of them with a diagonal step. And pictorially, it's as follows. So we take the first north step, we trace along the path, and then go to the first east step that's on one of these dark gray new diagonal boxes. And those are the ones we delete. We shift everything in between down, and then we replace that east step with a diagonal step. And so now that gives us a path that's a large new Schroder path. And it can, of course, have more than one diagonal step on the new diagonal now. And the inverse map of this is straightforward. It's just the same thing backwards. But we start with, we take the last D step on the new diagonal and then perform this procedure in reverse. And it's easy to check that composing in both ways gives the paths that you start out with. So this is a bijection. And to see why the if and only if part, the other part, why we have to have a north step in the beginning and an east step in the end, that's because you can see that this inverse map here is not surjective if we don't start with a north step, because it's taking paths with diagonal steps here and then transforming them only into paths that begin with a north step. So it's going to miss all of the ones that begin with a diagonal step or east step, which is only possible if nu does not begin with a north step. And a similar argument holds for if nu does not end in e. So
just to understand is when
Sure.
you say that, where does this begin? Is it beginning at the very first step, or is it like the second one?
So we always begin at the origin. So the first step is a north step. So
the first step is always a north step, but you need like the
Correct.
second step to be a north step also? Is that?
no, the first step is a north step. The second one could be an east step and then up and diagonal and
Yeah, but what I'm wondering is, so if you took this thing that you have on the right, it
Sure.
looks like this starts with a north step and ends with an east step. But if you tried to apply the algorithm to it, then I don't think you'd have a valid like new path.
Can you say that one more time?
So if you, so on the one on the right,
Yeah.
it looks like this satisfies the same property as the one on the left, where it begins with a north and ends with an east.
Correct.
But
yeah.
if you were to apply this algorithm, at least the way it looks to me, it seems like you'd be way too low.
If I applied it again?
Yeah, if you applied it again to that.
I see. Yeah, so this is not a small Schroder path now because it does have diagonal steps on the diagonal line.
Oh, I see. Yeah. So that, but if you were, yeah. If you, I feel like in general, if you delete the first north step, but then the second step is east, wouldn't you get too low? Because then you'd be like on the bottom.
Right. But if the second step is east, then the first east step on the new diagonal would be that second step that you just take immediately after. And so then that would be replaced by a diagonal step.
That would get replaced by that. Okay. Yeah. That makes sense then. Thank you.
Cool. Mm-hmm. All right. So another thing, moving, I guess, a little bit away from the large Schroder paths is this classic relationship between Narayana numbers and Schroder numbers. And so to extend some of that or see what happens with this new case is if we let Narayana nu I denote the number of nudic paths with exactly I valleys, the new Narayana polynomial, we can call it this, where the coefficients are these Narayana numbers. And a fact is that Narayana I is the number of nudic paths with I high peaks as well. And so these are, they count also the number of nudic paths with I high peaks, where these are peaks strictly above nu. And a cool way to see that is these little diagrams below. So if I have my high peaks, the potential places of high peaks circled in blue there, then the same, well, potential places for valleys, you notice that they're the same kind of, they're the same shape, and any two high peaks can determine a dic path down below. And then any, the corresponding set of valleys, if you map these down, one to the right and one down, you get these two, and those determine a nudic path as the valleys of a nudic path. And so you can see this bijective relationship here between nudic paths with exactly I valleys and ones with exactly I high peaks. So then we can define this new Schroder polynomial if we let Schroder nu I be the number of new Schroder paths with exactly I diagonal steps, or I d steps. And the claim is that it's the new Narayana polynomial shifted by 1. And so then we get this, new Schroder polynomial here, where the coefficients are the number of new Schroder paths with I diagonal steps. And this proof has a nice little combinatorial, well, it's a nice little combinatorial proof, so I think we can go over it quickly. But one thing to note is that the number of new Schroder paths doesn't change if we add a north step in the beginning or an east step in the end. So the number stays the same. We can add just lots of north steps in the beginning. That's not going to change the number of paths because those first north steps don't affect the count. So we can assume that nu begins with a north step and ends with an east step. And so each nudic path with I plus 1 peaks has I valleys. And we can then compute the following. So first, simply doing the shift in the new Narayana polynomial, and then applying the binomial theorem, of course, gives us this quantity, well, this polynomial in the middle here. And then noting that for every new Narayana J here, because each of those counts how many nudic paths there are with exactly J high peaks. And for each of the high peaks, we can take a shortcut and replace those with a diagonal. Because they're high peaks, we can do that without going below nu. And so for each of those J high peaks, we can choose I of them to replace with D steps. And then as a result, then the quantity here is exactly the number of, well, this quantity here is exactly the number of, well, there we go. It's the number of new Schroder paths with I diagonal steps. So a corollary of this is that, well, if you plug in 0 into this new Narayana polynomial, you get 1. So if you plug in -1 into the shifted one, you should get 1. And plugging -1 into the shifted new Narayana polynomial is gives us this result here. And that looks suspiciously like a Euler characteristic. And that's because it is. So in the classical case, this is obviously clear because as we saw in the slide earlier, we have the classical associahedron. Its faces were labeled by small Schroder paths. And then taking their alternating sum, we should get 1 because the classical associahedron is a polytope and has Euler characteristic 1. But then we can ask, well, what kind of a geometric object would these new Schroder paths correspond to, and be the faces of And this is, the answer to that is that it's the nu-associahedron that was introduced by Ceballos, Padrón, and Sarmiento. And to introduce the nu-associahedron, we need another combinatorial object. And that is the IJ trees, IJ forests, and covering IJ forests. So let's parse through some of these definitions here. So we start with a partition IJ, a partition of n, such that I is in, sorry, 1 is in I and n is in j. And so an IJ forest is a subgraph of the complete bipartite graph K1J. That's both increasing and non-crossing. So increasing meaning that I is less than j, and non-crossing being that no two of the arcs cross each other in the picture. And an IJ tree is a maximal IJ forest. And then an IJ, a covering IJ forest is an IJ forest that contains the arc 1 through n and no isolated nodes. So that's, let's look at some examples of that below here. So covering IJ forest, it has to have this big arc 1 to n, and then has no isolated nodes. So every node has a friend. So now those nodes are all covered by one of these arcs or attached to one of these arcs. So this is now a covering IJ forest. It's not maximal because even with this arc here, we could still add another arc in here to be non-crossing. Once we add that last arc in, we get the tree on the right, and that's an IJ tree. And the bar on the J, if you're curious about that, that's just to help distinguish between these elements. But it doesn't really serve a other purpose than that. Okay, but with this combinatorial object, well, how does nu relate to it? So since we're talking about the nu-associahedron, so a lattice path nu determines a set of covering IJ forests. And it does that as follows. So we can read the path northeast, northeast, east, northeast, east. Write that down here in blue. Add an east step in the beginning, add a north step in the end. And then that determines our set I and j above here, the partition of the number of steps that we've drawn, the partition of 10 here because we have 10 steps. And all the elements that are associated with the letter E belong to I, and all the ones that are associated with north steps belong to j. And now with this setup here, these nodes, they determine a set of covering IJ forests. And for example, this one would be one that is in that set. And with all of these covering IJ forests determined by this lattice path nu, we can put a poset structure on them with the following cover relation where T1 is covered by T2, if and only if T2 has all but one of the arcs of T1. So essentially that's reverse inclusion on the set of arcs. And you build this poset this way, and then we get the nu-associahedron. So this is how Ceballos, Padrón, and Sarmiento defined it combinatorially. They suggested the following combinatorial definition. So given a lattice path nu, the nu-associahedron is the polyhedral complex whose face poset is the poset of covering IJ forests determined by nu. So that's a bit of a mouthful there, but we're going to describe it instead of using IJ, covering IJ forests, we're going to describe it in terms of new Schroder paths in a bit. But first, some examples down here. So these are two-dimensional nu-associahedra. So for a lattice path here, this particular lattice path, we get this kind of a polyhedral complex. And for the one on the right, we get something pretty different. And notice that that's not even a pure polyhedral complex. So you get these cool polyhedral complexes. And it was realized by Ceballos, Padrón, and Sarmiento I mean, they actually defined it as the realization and suggested the combinatorial definition, but
we have a question in the
Yeah.
chat. Mark, do you want to ask it, or do you want me to read it?
I can ask it. So when you have a lattice path that doesn't begin with end and end with E, it doesn't seem like this actually gives you forest, because your I had to include 1 and your J had to include N.
So the way to get this, remember we started with a path here, but then we added an E step in the beginning and a north step in the end.
Okay.
To guarantee that, yeah. Good question though. That the reason we added that was precisely so that these trees would work out.
Okay. Thank you.
And when I say we, I mean Ceballos, Padrón, and Sarmiento did, because they introduced it that way. Sure. So this can be realized in several different ways. So it can be realized as a polyhedral complex that's induced by a certain arrangement of tropical hyperplanes. And this is actually the realization that they define to be the nu-associahedron and the ij-associahedron, actually, more generally. But then they also give two other realizations. One is that as a dual of a regular triangulation of a subpolytope of the Cartesian product of two simplices. And then also as a dual of a coherent fine mixed subdivision of a generalized permutahedron. And in some of my current work that I'm working on, but we haven't, or that I'm not really talking about today though, is that we have also another realization as a dual of a triangulation of a certain flow polytope. So that's something I'm pretty interested in right now. And another way to realize it is also a generalized graph associahedron on the path graph. So that's some current work. So it looks like you can generalize, or sorry, realize these nu-associahedron in multiple ways, just like you can realize the classical associahedron in many ways. But some cool properties I wanted to mention here real quick. So, well, one property is that the dimension is always equal to the number of non-initial north steps in nu. So we have two non-initial north steps here. And so this corresponds to a two-dimensional object. But another property is that the one skeleton can be given the structure of a nu-Tamari lattice. And this was actually what Ceballos, Padrón, and Sarmiento were studying, the geometry of nu-Tamari lattices when they introduced this nu-associahedron. So you can start with this bottom element down here and assign, I guess, I've drawn little arrows that are supposed to indicate the direction in which it's increasing, and that forms a lattice structure on this one skeleton. And that's known as the nu-Tamari lattice. And a really neat property of this is also that if nu does not contain two consecutive non-initial north steps, which it doesn't here, all the non-initial north steps are not consecutive, then it's a polyhedral subdivision of a classical associahedron. And there's a typo there. Add another S. But you can notice here that this is a pentagon that's being subdivided into some polyhedra. And pentagon, of course, as we saw earlier, is a classical associahedron. So somehow, or as long as nu doesn't contain these two consecutive non-initial north steps, then it's always a subdivision of a classical associahedron. And then furthermore, all the faces are Cartesian products of classical associahedra. So we have a pentagon here living inside of this big pentagon, and then another pentagon and some squares, which are Cartesian products of two line segments. So those are some cool properties. But we were interested in the face poset and connecting that with new Schroder stuff. So we showed that the face poset of the nu-associahedron is isomorphic to these two other types of posets. One, the poset of new Schroder paths, which we're talking about today, and then the poset of new Schroder trees, which I'm kind of leaving as an aside. And if you're interested, you can go look at it in the preprint. But I'll actually show you how the proof goes, because it's mainly just a translation between these objects and the cover relations. And I'll do that even before telling you what the poset structure on these new Schroder paths is, because I think that'll kind of explain where it comes from. So starting with covering IJ forest here, the way to translate it to a new Schroder path is you first take the halfway point of all the arcs, then you embed this tree in there. And then for each of the, you think of this tree as having a root up here, and then for each of its children, any left child gets labeled N, any middle child gets a label D, and any right child gets a label E. And if there are multiple middle children, they all get the label D. And once you've labeled the tree that way, then you can do a post-order traversal on this tree to read the new Schroder path from it. There is a little bit of ambiguity here, though, as it's drawn. How do we know that this E step here is actually a right child and not a middle child or a left child? And so that ambiguity is actually disambiguated in when you take this tree and actually put it to live inside of a grid, and that ended up, that's what we call a new Schroder tree. But this is the general idea of the translation between the IJ covering forests to new Schroder paths. You take this embedded tree, label it, and then do a post-order traversal to get the path. And with that, then you can translate all the cover relations once you have that it's a bijection and everything. And so we'll see what the cover relations are translated as well. And so that's how they arise. But before we can describe the cover relations exactly, we need this one more notion, and that's the notion of a horizontal distance on one of these new Schroder paths. So starting with a point P on a new Schroder path, the horizontal distance at P is the number of E steps that can be taken from P before crossing nu. So we start from P, take E steps, 1, 2, 3. And then if we took the next one, we would cross nu. So that's why the horizontal distance now is 3 from that point P. So with this little notion here, we can now describe the poset of new Schroder paths. And I suppose you can put other poset structures on there, but this is the one that is useful for us. So the cover relation here is that mu is covered by lambda if and only if lambda is formed from mu by one of the following contraction moves. So this looks a bit complicated, but some of these contraction moves are very easy. At least the first one is, you take any consecutive east-north pair, so a valley, you just bump it up into a diagonal step. And so that's a very easy cover relation there. And for the next two, we need that notion of horizontal distance. So starting with a point Q on this path, we measure the horizontal distance. Well, the Q has to be the beginning point of an E step, because our goal is always to take an E step and a north step and combine them into a single diagonal step. So we measure the horizontal distance here, it's 1, then we trace back along the path to the previous beginning of a north step, R, that also has the same horizontal distance. And once we have that, then you can perform this left contraction where you delete this E step, delete this corresponding north step, and then shift everything else to the right and replace the north step with a diagonal step. So that's a little bit complicated, but can be done. And the diagonal contraction is almost identical, but now you start with an E step that's followed by a diagonal step. And instead of measuring the distance from the beginning of the east step, you measure it from the end. So we get this poset once we do all these contraction moves. But something I want to point out is that, well, first of all, the resulting poset will be ordered by, or ranked by the number of diagonal steps, because each of these contraction moves just simply increases the number of diagonal steps by 1. And a useful fact that for later that we'll tuck away for right now is that only right contraction here increases the area under the path. And left contraction and diagonal contraction, they decrease the area under the path because we shift a portion of the path to the right and closer to nu. Okay, so here's an example of the face poset of this particular nu-associahedron here on the right, where the where we have all the cover relations as they were described in the previous slide, all the different contraction moves. So from this, it now follows that the Schroder I here counts the number of I-dimensional faces of the nu-associahedron. And now we can also conclude that the Euler characteristic is 1 because, well, we had that relationship between nu-Schroder paths in the polynomial as the alternating sum of them being 1. So we did all this work to get this complicated face poset described in terms of nu-Schroder paths. So is it useful for anything else? Can we say anything stronger using this? And it turns out to be really useful for answering the immediate follow-up question to, if you know something has Euler characteristic 1, you want to know if it's contractible, because contractibility is stronger and would imply that the Euler characteristic is 1. And so this describing the poset in this way actually was really helpful for proving contractibility. And so to do that, we need to briefly mention some things from discrete Morse theory. And that's the idea of a partial matching, and more specifically a Morse matching, which is a partial matching on the subset, given a poset, the partial matching in the poset is a subset M of P cross P, so that pairs in M imply that A is covered by B in the poset. And also every element A belongs to at most one element of M. And the partial matching has to be acyclic, or it is acyclic if the following is true, where there does not exist a cycle of this form. So starting with a B1 in the poset, you take the element down below it in the matching, and we write D of B as the down element from B. So let's work through an example here as we go through it. So B1 here, if I label it in the non-acyclic case on the right, B1 covers down B1, which is, if we follow along that pair in the matching, then that's covered by some B2, but that pair doesn't need to be in the matching. And then that covers some down B2 element, and this pair is in the matching, so it alternates being in the matching, not in the matching, and so on. And then this is covered by some element B3. Then we go to down B3, and this is covered by B1. And so now we end up with a cycle if we trace along here. And so this forms a cycle, so this particular one is not acyclic on the right, whereas the one on the left happens to be acyclic. And any elements that are missed by this matching or not in any pairs, they're called critical elements. And so the main theorem of discrete Morse theory, this result in topological combinatorics, it states the following, that if we have a polyhedral complex and M is an acyclic matching of the face poset without the empty face, so without the bottom element of the poset, and if Ci is the number of critical I-dimensional cells of delta, then the following are true. That if the critical cells form a subcomplex, delta C of delta, then there is a sequence of cellular collapses leading from delta down to delta C. And in general, the space delta is homotopy equivalent to delta C, where delta C is a CW complex with Ci cells of dimension I. So a quick example, just very quick, is a 2-simplex here. This is the face poset without the bottom element. We can have this acyclic matching on here, and then it has one element of dimension 0. So that is not covered in the matching. So the 0-dimensional cells, critical elements, there's one of them. And so what this says, this theorem, is that we can now perform cellular collapses on this 2-simplex to get it down to a single vertex, which we, of course, intuitively know that we can do. So this is contractible. And the contractions, or the cellular collapses are given by each of these pairs in the matching. So that collapsing there was this first pair, and collapsing, the second one was, sorry, not that one. The second one was that pair, and then the last one was that pair. And so we end up with a single vertex. So the original space, the 2-simplex, was homotopy equivalent to a CW complex with one cell of dimension 0, which is a single vertex. So we're going to do the same thing for the nu-associahedron. We just need to find a Morse matching on the face poset. And the matching we're going to use is the following. So let M be the pairs pi sigma, such that pi is formed from sigma by replacing with east-north the first D step not preceded by a valley. And I'll show an example of that in a second, but here's the 3 things that we just need to check: that it is a partial matching, that it's acyclic, and also that there's exactly one critical element of dimension 0. And then the result follows. So here's the matching, the partial matching. We start with, say, this path here, and let that be sigma. And so pi is formed from sigma by replacing with east-north the first D step not preceded by a valley. Okay, so that is a bit of a mouthful, but take the first diagonal step here that's not preceded by a valley. That's right there. Replace that with a valley. And so then we get this path down here. So then this pair is now in the matching. And you can check that the rest of them also satisfy this, but that's how we check that one element or one pair is in the matching. And notice that now from this pi path down here, it can't cover anything else in the matching because there is no diagonal step that's not preceded by a valley. We introduced this valley in the beginning, so it can't cover anything else in the matching. It can't be involved in another pair. Okay, and that's essentially just the first case that we just checked that can't happen. And these are the cases we need to avoid in order to guarantee that it is a partial matching, so that no one single element is in more than one pair in the matching. So we essentially just did this case because pi sigma in the matching means that any D step in pi is preceded by this valley east-north. And the second case can't happen by construction because sigma, well, you can't take form two different paths by this one operation. So that can't happen. And then similarly, the last case can't happen just because if we form if pi sigma is in the matching here, then pi has no values or d steps before the valley formed from sigma. And the same thing is true for pi if we look at it in comparing it with tau. So it follows from that actually that tau and sigma have to be the same path. And so none of these cases can happen. But in the interest of time, let's just quickly run through this last bit. So M is acyclic. We just need to check that this kind of a cycle can't happen. And one thing to notice is that the area goes down by 1/2 at each of these points, all the way down, except for the in-between portions here. So at every step down pi1 to, from pi1 to down pi1 and pi I to down pi I, the area decreases. So then the in-between steps, because it's a cycle, it has to begin with the same path as it ends, the area has to be preserved. So the in-between steps here then have to increase the area by 1/2 and so on. And now we untuck that fact that we tucked away earlier, is that only the right contraction move does that. And so that means that we have to have right contraction moves in between the here, and the right contraction down pi1, pi2 occurs at a valley after the, if it occurs at a valley after the first valley of down pi1, then the cycle has to end at pi2, because we go down and then go up to a potential pi2 here. If this is pi1, you can't go down from pi2 any longer. It has to, if that's part of the matching, it has to go up. And so that can't form a cycle there. And if the right contraction occurs at the first valley, then pi1 equals pi2. So essentially the only possibility is that we go down and come back up, and that's not a cycle. So M is acyclic. And essentially the final slide. We just need to check now that there's only one possible path here that doesn't get covered by this matching. And that's always going to be this path of all north steps and all east steps following each other. Because this doesn't have any valleys or diagonal steps, it can't be a part of this matching at all. And so there's exactly one element of dimension 0. So this is homotopy equivalent. The nu-associahedron is homotopy equivalent to a single vertex, so it's contractible. I know we kind of rushed through some of the details of that in the end here, but hopefully you got the gist of the idea at least. And because that's all I wanted to say today. So thank you, and I'm happy to take any questions.
Well, thank you. Let's thank the speaker first of all. Yeah, does anyone have any questions? See a few people saying it's a nice talk, which it was.
Matias, could you maybe just share a bit about the connections with flow polytopes?
Oh yeah, so that's actually really fun. So we have these families of graphs that we're looking at. So if I draw one here, if you know the lingo, this is a Pittman-Stanley graph, and then you can draw these cool other arcs on here. And you get these really cool graphs, and they're called caracol graphs. That's my butchering of the Spanish, but it means snail, and because they look like snails. And so this is a particular generalization of that. But if you take, generalize these in a particular way, you take the flow polytope over these graphs. And so that's a polytope that you get when you put a flow in here and treat these edges as directed towards this sink here. So this is the sink where everything flows out of, and here's the source in the beginning where everything flows in. So you take the flow polytope over this particular graph, and then you triangulate it and take the dual graph of that triangulation. then you get the nu-associahedron for particular choices in degrees for these vertices in between here. You can pick the in degrees so that you get the nu-associahedron essentially as the dual to the triangulated flow polytope. And that was actually what we were studying to begin with, and this was kind of a side project, but yeah. Flow polytopes are really cool.
Awesome, thanks. Are there any other questions?
This is sort of a broader question, but your Morse matching seems like it's a very combinatorial Morse matching. Is there a hope that you could apply it to some other interesting complex or some other interesting poset, I guess, in this case?
Ooh, I'm not sure. It seems very specific to new Schroder paths. And
Right.
if they happen to index the faces of something else, then perhaps, but I'm not actually sure about that. That's interesting to think about.
I'm wondering if there's like a connection here to some of these like alternative forms of parking functions or something.
Yeah.
Parking functions or some.
Yeah, so generalized Schroder theory has been studied in certain, not quite to the full new generality, but to certain rectangular cases that's been studied with connections to parking functions there, and also QT combinatorics or QT Catalan combinatorics. So there certainly might be connections that direction.
Awesome. If there are no more questions for Matias, before we thank him one more time, I'd like to invite you all again to come back next week. And next week we'll have Elizabeth Kelly, who will be talking to us about something that will be shared through an email sometime soon.
Probably snake graphs. If you're interested in cluster algebra, she works on these really cool objects. I don't know for sure yet, but she does snake graphs and cluster algebras and just like really jazzy things.
Awesome. So if you're a fan of cluster algebras and snake graphs, please join us next week. If nothing else, let's thank Matias one more time.